Good afternoon, this is Brian with Quanta Engineering, and I have a tutorial on how to build a sheet metal box that's got some Prism type features, such as what's being shown on the screen. This is a box that was in one of my Facebook Solidworks forums where a guy was asking how to model it, and I thought I'd just put together a quick tutorial video. The challenge is these facets on the corner. So if this is an actual sheet metal part, then something is going to have to be broken in the sheet metal part and then welded together in the final step. And if it's made out of plastic, this could be actually molded. So I would guess, based upon this fairly low res picture I'm looking at, that this is probably originally a plastic part. It could even be a fiberglass part, but either way, to make it out of sheet metal, we'll just get into it and show you how. So the first method I used was with a 3D solid that's been converted into a sheet metal part. And so I'm just going to show you in this part how to do that. What I started with was with a box, just a standard extrude. I picked some basic dimensions, 10 by 15 by 8. I drafted those faces on the side to create the prism feature, and then I created a sketch and some planes at the corners so that I could intersect the edges, intersect with those vertices, and then split away all those corners to create the prism. Now, something to be aware of is that when you do a draft, you can select the draft out of the tree and double select it and get to the edit of the angle. But what you can't do is select on the drafted faces to edit the angle. So if you want to create drafted faces that you want to edit, maybe the offset, not so much the angle, such as controlling the distance here horizontally from this lower edge, then you'd want to do like an extrude cut. Then I shelled it, and I only shelled it because I like to make sure that my models that I convert from 3D to sheet metal actually look somewhat like sheet metal parts before I actually convert them. Technically, I wouldn't have to do the shell. I could just leave it alone. And then I do my sheet metal conversion. Now, in this particular part, I haven't done it yet, so I just come over to the sheet metal workbench, convert to sheet metal, and you just grab your top surface that's fixed, and then you come in and you grab your bend edges. In this case, it'd be all the top edges. You want to make sure. Now, the downside to shelling it is if I accidentally grab the inside edge, it'll give me an error. So you got to make sure that all your external edges are selected. And then from there, I have to make a decision. Am I going to use the side flange for my bend for the triangle, or am I going to use my end flange? So I'll show you both. So automatically, SolidWorks identifies that there is an extrusion or exclusivity here where this edge here cannot be included as a radius. It's a gap, so that's going to be your ripped edge, and it's populated in my ripped edge down here. And so continue to move around. So on this side, I'm going to do it where I've got the side flange. Here I'm going to go ahead and grab my end flange to be my bent feature. And then from here, obviously all the surfaces highlight. From this point, I can actually come in here and control a few other features. The gap on my corner defaults. If these were 90-degree bends, then I could start playing around with my overlaps and underlaps. And the only reason I'm not going to do that here is because what will happen is it'll actually extend my sheet metal part past, and it probably won't preview it for me. Oh, there it goes. It shows me. There it goes. It gives me a preview there where it's funky, it's overlapping pretty bad. So I'll just do the open butt joint, and then I'll give it a distance. This is basically 2 millimeters, but I can also just do the thickness of the sheet metal. The gap, I like to use either the thickness of the sheet metal or roughly half. And then my overlap, that's up to the individual engineer or designer. I'm going to do override my default parameters for my relief. If I do an O-brown, I get this nice curved feature in the corner. Problem is, if you rotate in here, you can actually see a little bit where the corner, ever so faintly, the bend radii actually interfere. And it's because of the nature of how we're developing this model, where it's got a 75-degree bends instead of 90-degree bends. I could play around with it. There's actually a lot of different ways to fix this, but changing this ratio doesn't really fix it. You can bring it all the way down to 0.1, and even then you'll see it brings it back, but it doesn't fix it. It still leaves just a little bit of interference in that bend. Even if I were to do 0.01, 0.05, I should have known that. So 0.05, and I still have an issue where the bend radii are touching each other. And ultimately, I'll just bring this back up to 0.5, and I'll get this error. And it's just telling me that the bend faces are fused together. It's not the end of the world. I actually can show you how I did fix it, so where the model does work. Or what you can do is you come in here, and I've built the 3 different versions of this configuration with an around, a rectangle, and a tear. So if I do a tear, what happens is it actually rips apart the sheet metal, and for whatever reason, Solidworks doesn't have enough complexity built into this feature to where it knows to put a radius in these corners or anything like that. You can go into the model and create little base flange tabs where you finish out these features. That becomes pretty time consuming. You get a very similar type of corner feature with the rectangular. It's just a little bit less pronounced, okay, but same issue. And then if you do the O'Brown, the way that you fix it, one way that you fix it is you do a cut feature where you come in and you actually project the geometry of the interfering bends, and then you extrude them past and leave behind the other faces. And then now, at least by doing it this way, I can flatten my part. Otherwise, I wouldn't be able to. Now, the warning still exists. Notice it's a warning. It's not an actual failure. It's just telling you, hey, it's just saying that it can cause problems. So from there, that's one way to create a part like this. The only thing I don't like about this is whenever you select on a converted solid and you try to edit the underlying features, you can't. It'll just kick you back to the conversion level. Everything that's before that is inaccessible from the 3D space. You have to go back to the tree to select it. So if you have a bunch of different drafts, or if you have a bunch of different features like holes and things like that, you don't want to put those in until you've converted it to sheet metal, which can be a problem. I prefer to build it directly as a sheet metal part. And a sheet metal part, I've done it a couple different ways, or I start out with a couple different things. First off, I start with the flat base flange, and then I did an edge flange. Here, they're all just at 75 degrees. It's same length, and then what I did was I made sure that the flange position is set to intersect from or bend from a vertical sharp. And the reason is because I want to make sure that the outside faces, the intersection of those faces, is the same as the dimensions of the original flat. And so if I would have done a material inside or outside, or any of these other ones, it would have changed things. And they tend to be a little funky when you move away from a 90-degree bend. From there, I came in, dropped a plane on the corner, and then I measured that plane to the outside face, and that gives me an angle, and that angle is roughly 44 degrees. In reality, no sheet metal shop is going to bend it to or form it to 44.007. So what I did was I just formed it at 44 degrees. In this particular case, I bent it from the end flange, not from the side flange. The only thing you have an issue with is here, the bend doesn't extend all the way up to the other bend, and that's just because of the interference. It has to have relief, and because you can't have those two bends interfering with each other or extending and touching each other. You could have a rip feature, but generally speaking, you want to have a gap. In reality, when you make this, you'd want to have a clearance between these features. And the way that I solved that was I actually unfolded the part. I came in on the other corner here, and I actually took a cut feature, and I drew a sketch, projected the edges, cut it down, and then I folded it back up, and now I have a corner that actually works. Now, If this was not going to be a welded corner, I would have put a radius relief into the top flat, just so that there's no propagation of cracks. In this particular one, it's going to be welded. I'm not worried about it. No big deal. And again, it's just a demonstration. And then from there, your part is pretty close to being done. At any point in here, I can flatten it, I can unfold it, etc. The last method that I was going to show is basically like a French door effect, where you could take an edge flange all in one shot. And what I did was I didn't really talk about it in these other ones, but when you select your edge, you come in and you edit the flange profile. And here, instead of it, normally it would come out perpendicular to the base edge, which is the projection of the base geometry, and then it would be a rectangle. And here what I've done is I've just drawn a new line in its place and drawn an intersecting line or a line in the middle to be like a symmetry. And then I have a line here that's actually a symmetry between the two corners. And then from there, I repeated it for the other edge and move on with life. And then I get this nice clean effect. This is obviously, while it makes it nice to where you have a known radius for your bend, it makes it more difficult because now you got a bead right down the middle. And so if a guy is going to try to grind that smooth with a flap disc or something, now it's going to be much more difficult to get this part to be clean versus if you were to do it in the corner and then just radius it with like a belt sander or something. So yeah, that's kind of the methodology I would use for modeling a part like this. This part, the reason I like building in sheet metal directly is because now when I select on any of those features, I get directly to the feature I was looking for, I built. And that way, anything I do, I'm going directly to it. I'm not going back to the conversion. So I hope you learned something from this. And if you have any questions or you have any content you want to see, by all means, comment below. And we will do our best to put together like a tutorial video or show you how SolidWorks can be used to solve your problems. This is Brian with Quanta Engineering. Don't just design things. Be engineered.